Okay, in this video, I'd like to take our previous results, which took us from this potential of a finite charged rod of length L, where we were located y units above the rod and a units from the left side of the rod and L minus a units from the right side of the rod. We took the potential, remember, and we actually did two derivatives. We did a ddy, which is sort of a derivative rate of change as we leave the rod, and we got this first horrible mess. And then we did a DDA, which means we're going to try to move the little black stick to the right and therefore change our A value, and we can get a rate of change of potential. And that gave us this. And it didn't have the minuses. Remember, the minuses actually were not part of the derivative process. Those are there along with these unit vectors to represent direction. So what we're saying is when you adjust your v away from the rod, that's y direction, you pick up a field in the opposite direction. In other words, you don't pick up a field, but the rate of change of v in the positive y direction is equal to the opposite of the field in the y direction. And as you go left and right, the rate of change of left and right potential gives you the opposite of the field in that direction. So I wanted to show you an alternate way of thinking about the same problem, and I think it's going to be a little bit eye-opening, but this video is technically optional. Okay, so going back to this, let's take a look at the geometry of the situation a little bit differently. If we have our rod L and we have our point P up here, and this distance here is just called, let's call it R sub L. It means the distance from the left end of the rod, and this distance here is called R sub R, or capital R. Let's use capital letters for our subscripts. So lowercase r just meaning we are a distance away, just like we always call r our distance away. But these are from the left and right endpoints of the rod. So that the rod actually terminates at these little blue balls. And so distance from point to the left blue ball is r sub L. The distance from the point P to the right little blue ball is r sub R. Okay, so you'll notice something. There's two right triangles. There are two right triangles here. So the first one has A and Y with hypotenuse r sub L. And the other one has sides L minus A and Y, and the hypotenuse is r sub R. Okay, so if you just kind of go back to the potential here, it says K lambda ln, and there's so much garbage, but look how it cleans up when we pick an alternate measurement system. When we see this expression, the square root of L minus A squared plus Y squared, that's really just R sub R. I wrote that. Sorry, I think that was on mute. I just changed the square root of L squared plus square root of L minus A squared plus Y squared to R sub R, and then it's plus L minus A, and then the bottom is simply this one here. Let's pick another fun color. How about we pick this neat green? That thing is just R sub L, and then it's plus or minus A. So real simple looking now. Look at that. Wow. Okay. So I don't really want to get too carried away with that, but I just kind of want to show you that, there are simpler ways of writing things. And if you see a lot of square roots going on, it could just be that you picked a bad coordinate system, and maybe you should have stuck with a spherical type idea. But anyway, there are other ways we could write this. I want to look, though, at the other formulas and talk about that same thing. Okay, so another kind of small, I actually shrunk them, so I'm gonna grow them again here. So Mr. Short's gonna grow that up a bit. I want you to just look at the geometry, and I'm just gonna retitle a bunch of stuff. Okay, so let's import our little geometry picture that we just had here. Let's grab this little guy and group it and bring it in to this page. I think we'll be glad we did this. Okay, you'll notice that we have here a y over square root of L minus a squared plus y squared. What a mess, right? Just this top part of this first fraction inside this huge answer. But you might recognize this. We just got done calling this down here r sub r. What would y over r sub r represent? Well, y over r sub r, if you go back to your original drawing, y over r sub r is the sine value of this angle right here. So if we call that theta sub right, that's just sine theta sub right. Interesting. So this is all just, I'm going to go ahead and write my e sub y all over again in a much tidier notation. Negative k lambda, and then I have sine of theta sub right. So that's just sine theta of r. And then on the bottom, we've already seen this denominator before. It was just basically r sub r plus L minus a. See how nice that looks? Okay. And then we have minus, okay, and then the other one, the other fraction here on the top, I'm circling it with a squiggly cloud, that's y over a squared plus y squared. And that kind of reminds us to look over at this triangle. And you'll notice that's really just sine of the angle in this corner. So let's call that theta sub L. Theta sub L. So this would just be sine of theta sub L all over r sub L minus a. So this just greatly simplifies everything when you start looking at that. And here's another thing that's interesting. Now you're starting to see those sines and cosines that we often see with vectors, right? So these weren't part of our scalar field, but you can start to see this has that component sort of feel to it with the sines and the angles and the direction and all that. Okay, you could also write e sub a in a similar way using cosines. So let's do that. So e sub a. Remember yesterday I also said for y you can call that r, and for a you really could call it z, according to the traditional convention of cylindrical coordinates. But I'm not too interested in what letters we pick today, just trying to notice the relationships in these large crazy expressions. And then we have negative k lambda for this one, and this is going to be in the a direction, also known as the z direction. Okay, so we have a minus L all divided by a square root of L minus a squared plus y squared. So that is technically the cosine of theta right, cosine of theta right, and I kind of wish I left a negative in the front here. I'm going to put a negative right there and call this L minus a. Just because you'll notice that L minus a is the name of the adjacent. So that way I could put negative cosine of theta left, or theta right, I mean. And this is all over, same denominator, r sub r plus L minus a minus, and then we have right here a over square root of a squared plus y squared. That's just cosine of theta left. R sub left minus a. So there you have it, the horizontal and vertical component kind of idea there. Pretty neat. It's kind of unconventional to use a system that has a theta L and a theta R, you know what I mean? Like you probably wouldn't want to have a theta R and a theta L together. So you may actually go on to say, well, what does theta L have anything to do with theta R? You know what I mean? Are they related to one another? Could we use trig identities to relate theta R to theta L? And there's other things we could approach it with. But I'm not sure we're that interested in going too far with this. I just wanted to show you that alternate ways of defining things can make a simpler life for you. All right.